Have you ever tried to add up a list of numbers that just keeps going? It feels like it would be impossible, right? Well, today we are going to pull back the curtain on a simple but super powerful shortcut for that exact problem. It's all hidden inside a cool concept called the geometric series.
So, first things first, let's really wrap our heads around the problem. We're staring down what looks like an endless chain of numbers to add up. Is there really a way to solve this thing without, spending the rest of your life with a calculator? Okay, take a look at this. How would you even start to solve it if this list just kept on growing? I mean, you could grab a calculator and go for it. 2 plus 6 is 8, plus 18 is 26. But what if there were 100 terms, 1,000? No way.
And that, right there, is the heart of the problem. Doing it term by term is just painfully slow. And if the series genuinely goes on forever, then it's not just slow, it's literally impossible. There's got to be a better way, right?
You bet there is. I'm about to show you one single beautiful formula that can knock this problem out in seconds. And honestly, this isn't just math, it's kind of like a superpower. Now, before we jump to that amazing shortcut, we need to get on the same page with a couple of key definitions. It'll just take a second, and it'll make everything else make perfect sense.
First, let's do a super quick recap of something called a geometric progression. All this is a sequence of numbers where you get to the next one by multiplying by the same number every single time. So for our example, 2, 6, 18, what are we doing? We're just multiplying by 3 at every step. That number, the 3, is what we call the common ratio, or just R for short.
Okay, now watch this. It's a tiny change, but it changes everything. When you take that same progression, 2, 6, 18, and you swap out the commas for plus signs, bam, you've just created a geometric series. It's not a list anymore, it's a sum. And that is the beast we're trying to tame.
All right, with those definitions locked in, it's time for the main event. Let's unveil the tool that's going to do all the heavy lifting for us from now on. This right here, this is the hero of our story. One clean, simple formula that can take a geometric series with dozens, hundreds, even thousands of terms and give you the total sum almost instantly.
And here it is. Sn equals a times, in parentheses, r to the power of n minus 1, all of that divided by r minus 1. Let's break it down. Sn is just the sum we're looking for. A is the very first number in your series. R is that common ratio we just talked about. And n is just how many terms you want to add up. That's it. Pretty neat, huh?
So why does this work? Well, think about it like this. An arithmetic progression, where you just add the same number over and over, grows in a steady, straight line. But a geometric progression, where you multiply, that thing explodes upwards. That's exponential growth. Our formula is perfectly designed to capture the total sum of that wild, compounding growth in one clean calculation. Okay, let's put this formula to the test. Theory is awesome, but seeing this thing in action, that's where the real magic happens. We'll walk right through it together. Remember this guy from the beginning? Seemed like a real headache before, but now we have our secret weapon. Let's find the sum of just the first 5 terms. Okay, step 1 is just identifying our variables. So a, our first term, is 2. The common ratio, r, is just 6 divided by 2, which is 3, and n, the number of terms we want, is 5. Now we just plug those numbers right into the formula. So the sum is 2 times 3 to the power of 5 minus 1 all over 3 minus 1.
And boom, the answer is 242, just like that. No adding over and over, no chance of making a silly mistake. Just a quick, clean, and confident answer. That is the power of this thing.
Let's run through one more, just to make sure this is really locked in your brain. This time, we'll find the sum of the first 6 terms of a totally new series. 5 plus 10 plus 20, and so on. This will really build up your confidence. It's the exact same process. The first term, a, is 5. The common ratio, r, is 10 divided by 5, which is 2. And we want the sum of n equals 6 terms. We pop them in the formula, do the math, and you get 315. See how easy and systematic that is? Identify, plug in, solve. You can now basically handle any finite geometric series that someone throws at you. But look, this isn't just some abstract math trick for a test. Let's take this formula out of the classroom for a minute and see where it actually shows up in the real world. You might be surprised. Before we do that though, just a quick heads up. As you start using this, there are a few common tripwires people fall into. The biggest one is forgetting that n is an exponent on the r.
People also sometimes mix this formula up with the one for arithmetic progressions. And remember the golden rule. This whole thing doesn't work if the ratio r is exactly 1. Just keep an eye out for those.
So here's why this actually matters. This formula, it's the engine behind how so many things grow exponentially in the real world. It's how banks calculate compound interest, turning your small savings into a big pile of cash over time. It's used to model population growth, to figure out returns on financial investments, and even to track things like radioactive decay or how fast bacteria spreads. It is truly everywhere.
So let's just sum it all up. A geometric series is simply adding up the terms of a geometric progression. Its signature move is exponential growth, and mastering this one formula is a huge skill, not just for passing exams, but for actually understanding how the world around you works.
We've totally nailed how to add up a specific number of terms, like 5 or 6. But that leads to a really wild final question. What if n isn't a normal number? What if n is infinity? Is it even possible to add up an infinite number of things and get a real finite answer? We're going to explore that mind-bending idea in our next explainer.